Hello everyone. You can hear me, right? In this class, we're gonna review the content we talked in last class, and then we'll have the exercises on MOOC. I'm not sure if everyone log in MOOC today, but cause it's the first time you're finish this exercises. So this time I'm gonna give you more time to log in and finish the questions. So okay, in last class we just learned some important things for operating systems. Uh, there are three topic or three things you need to understand. The first is that about the description of the operating system. You have to understand the operating system can play two important roles. And if you are a common user or you from the you look at the operating system from the perspective of some application programs, you will view the operating system as an extended machine which can provides you some services about the operations to on the I/O devices or the permission to access the memory, uh, etc. So, but we are students majored in computer science, right? So, you cannot just uh, stand from the perspective of a common user or application programs. So, as a designer of the operating system, you need to dive in to understand what the operating system needs to do on the resource management. So the second role of the operating system, you should understand how to manage all the resources on computers. So that's what I emphasize all the time. The operating system is a resource manager. Everything is about resource management. The resource includes hardware resources and software resources. So this is the first important thing you need to understand. And the second one is that we have two different modes in CPU. The two different modes include kernel mode and the user mode. So I hope you can recall what kernel mode means. The CPU has two modes to run the program. If CPU is in kernel mode, it means the program or the software or the code running in CPU have the permission to access all the have the permission to execute all the instructions of the machine machine set. So uh, basically, operating system is the only software because it's a special software. Uh, Operating system is the only software who have the uh, full access to all the instructions and all the application programs. They can only run in user mode. It means if a application program wants to access some I/O devices, the request will be denied by CPU because the application program doesn't have such permission. It has to use some user interface program to make some system calls to the operating system and let the operating system to do the operation. So the two basic modes you are very important for us to understand the principles of operating system. This is the second topic you need to understand about the kernel mode and the user mode. Also, we explain about the two different ways to share resources in the computer. We have a set of resources, hardware resource and software resource. Excuse me. The two different sharing ways are we can call them we can share the resources in time or in space. You need to memorize the typical resources which are shared in time or and in space. For example, CPU and printer, they are shared in time. It means the multiple programs in memory can take turns to use the CPU to run some codes. So the main difference between the two sharing ways are you use the resource, you use the whole resource, or you just can use the part of the resource. If you can occupy the resource, the whole resource, at a moment, then it can be or you should use this. You should take turns or to use this time multiplexing resources. Cost not more than one, no more than one program can stay in CPU or printer. And for the space multiplexing, the typical resources are memory and disk, because you can multiple programs can stay in the disk or memory at the same time, but they can use only part of the resources. So basically, that's the three important things you need to understand through the last class. And I'm not sure if you are ready to do the exercises on the MOOC, because I just, hold on, I need to log in WeChat. So I'm gonna give you 1 minute to check your WeChat, to check the mini program called MOOC on WeChat. And if you are ready to, if you are already in that class, you can give me a signal. You can type 1 or anything in Tencent class, and then I'm gonna publish the exercises on WeChat on the mini program called MOOC. So are you ready? Okay, so someone already in. Give me some information about the login. Okay, so now I'm gonna publish the exercise. You just check them on WeChat, okay? You have 8 minutes to finish them. There are only four questions. Only four questions you need to answer. I give you some I give you some extra time to get familiar with the platform, with the operations on WeChat. I think the time is totally enough for you to finish all the four questions, and the answers to that questions I just uh, gave you a review. Just for very simple questions. Did you see the questions? Uh, did anybody just submit your answers? Because I haven't seen anyone. You can see the questions, right? You just need more time to answer to it. No? Okay. Nobody submit yet. I don't think you have much time to finish them. You, you have to submit them before the deadline. Otherwise, you will get 0 for this exercise. Okay, time is up. Let's come back to Tencent class. And cause some students have the issue of time difference, and they are gonna take this exercises this night tonight. So if you are wondering about the right answers to those questions, I will explain them in next class. Okay, now let's just start learning the new content for today. So as I say, you already know that operating systems can act as as an extended machine and a resource manager. And you also know that there are two different modes called kernel mode or supervisor mode and the user mode in CPU. Also, you know the resources can have different ways to be shared among multiple programs in the same computer. Um, that's the basic concepts for this course. And the next section is about the history of operating system. So we're gonna take a brief review about the history of operating systems, and after that, we'll explain the computer hardware, because the operating system is about resource management, right? We have to understand the objects to be managed. So these are the main contents for today. First, let's take a quick look about the history of operating systems. So I think you all know that there are five generations of computers, right? From the first computer, uh, the five generations of computers just have evolved. Um, Actually, mm, there are no clear generations about operating systems, but because operating systems are high relevant to the hardware, to the computer, so we can roughly divide the history of operating system as the same generations of computers. So you can see the uh, for the first generation of computers, there are basically uh, no any concepts or about operating systems, because operating system is used to manage the resource. Usually, it implies that the resources are shared by multiple programs. But for the first generation of computer, the program. Actually, there is no program. It's just some steps of calculations will running on this computer. So those procedure runs on the computers. They just uh, they can use all the resources on in a not sharing way. You can see this picture just shows us the ENIAC, the famous the famous computer in 1945, and it's very large. It has, because it's built with vacuum tubes, so we need a very large space to locate it. Also, except ENIAC, we have ABC, Z3, some other computers, but they are all built with vacuum tubes, and they are all primitive and run very slow. Uh, as I said, there is no program, no concept of program, because everything you need the computer to do, it's not written in some programming languages for uh, easily understand, which can be easily understood by the common users. If you want the computer to do something, you have to uh, punch them in the cards, or use a board to list all the steps about the calculation, and put the plug board or the punched cards into the computer to get the final result. And it usually it might need a couple days to get the final results. So this is about the first generation of computer. And for the second generation of computers, they are built with transistors. You can see the volume just gets much smaller. And in this generation, we can there are some we have the concepts of the programs. We can use some language to write some for example, Fortran or assembler,
uh, it's uh, it's much easier than the machine language. It is much easier to understand these programs, but actually we have to uh, use some special ways to let the computer to input these programs into the programs. They are not just we can't just type them in through the keyboards like we do today. We have to punch them on cards and use some special machine to read from the cards to some tapes. So in this generation, you can see uh, a raw operating system. Some raw operating systems just emerged just like FMS and IBSYS. Where we have some figures to show you how the batch system, the how the batch system, I mean the raw operating systems work for this generation of computers. So you can see we first the programmers they have to write the program on put the program onto the cards onto the punched cards, and then the computer cannot read directly from the cards to get the program. It has to the program on the cards has to be read through the card reader and transfer the program, the text on the cards onto the tape. And 14 special computer called 1401 was responsible for this job. 1401 will read a lot of punched cards, which uh, uh, just this a lot these cards will include a batch of jobs, more than one job. I mean more than one programs to run in the computer. So uh, this special hold on this you can see this computer just read from the punched card and put them onto the tape, put the programs onto the tape. So on this tape, on this input tape, it just includes multiple jobs, a lot of jobs, not a lot, just a batch of jobs to be executed in the computer uh, which is responsible for the processing for the program for the execution of the program. So the operator needs to uh, input this tape to this computer called 1794. So this is the second computer in the whole in this system. We have three computers to handle a batch of jobs in the second for this batch system. 1794 is responsible for the calculating for the processing for the execution of the programs, and 1410 these two computers are you responsible for the input of the program and the output of the result. So you can see 1794 got the result, finished the execution of the program and got some results. It just output the results onto the output type, and then we need the operators to carry it. It means you have to walk from this computer to the next computer, to the next computer, and it just cost a lot of time because we needs a couple maybe a few minutes to arrive from the last computer to the next computer, and then operator will put the output tape onto the second 1401 to output the results to the printer. And here was are the materials with the results which can be understood by people. So you can see the whole process was very time how to say it's just waste a lot of time, right? We need three computers to charge the three different process, uh, input, and you process, and then you output the result. So this is basically this is very low effective, and then we move to the third generation of computers, and in this generation you can see we have two important technologies which can support the typical operating system. It's called multi-programming and spooling. Uh, Also, from the perspective of the hardware, this generation of computers are built with ICs, integrated circuits. So you can see the volume was had been getting much smaller than the even than the second generation of computers. And for this generation of computers, usually they are employed by by some companies and factory. Yes, just by some companies and some academic institutions. But not much. There are few people. There are few common users can who can uh, who can afford the this generation of computers, and it's not popular for the families. So let's talk about these two main technologies. Uh, it's called multi-programming and spooling. The first one, multi-programming, that means we have some technologies to support the computer to uh, to run more than one program during the same time. So it means the memory of the computer can be shared by multiple programs. But before the third generation computers, even in the batch system, you can see the type, what the programs on the type on the tape was what was transferred to the 1794, right? And the 1794 for 1794, it can only run just only one program at the same time. During the same time, it cannot provide the computing service for more than one program. But in the third generation of computers, the computer can let more than one programs stay in the memory during the same time. But there is only one CPU. So it means these programs in the memory, they have to follow some rules to use the CPU one after another, because we know that CPU is shared in time but not in space. They have to take turns to use CPU one after another. And this is the what multi-programming technology does. It means it can it allow more than one programs stayed in the computer during the same time, and they can compete for the only computing resource in the in the computer, I mean CPU. And for the second technology, if you recall the steps to the steps of batch system in the last generation of computers, you can see we have two different computers to handle the input and output operations, right? There are three computers in the whole system. So it's very ineffective. So for the third generation of computers, we have this technology called spooling. It means simultaneous peripheral operation online. Online means we don't need two separate computers to handle the I/O operations. We can use this software to control the whole I/O operations on the same computer. On only in this in this single computer, we just need to run some software called spooling to control the I/O operations for more than one programs. So these two key technologies just support the modern operating systems, and we'll discuss them in more details in the following chapters. For now, you just need to understand that with these two technologies, we can a lot of typical operating systems just emerged to match the different resources in the same computer, such as Unix, BSD, System V, and the typical computer which employs this operating system is called IBM 360. So you just need to have a quick look about this, because very soon we just move on to the next generation of computers, and this one, this kind of PCs, I was very familiar with this kind of PC because I once used to some computers like this when I was in college, when I was in university. But for you, maybe you haven't seen this personal computers before, because anyway, this fourth generation of computers are were getting much smaller and smaller, and they are built with large scale integration circuits. The typical operating systems for this generation are MS-DOS and Linux and Mac OS. So you can see they are developed by three different kinds of companies. For Linux FreeBSD, you must know they are usually open resource, open coded. You can check some source codes based on the Linux kernel. Also, there are some they have free versions, and they have some versions charge us some fees. But for the other two series, this is is developed by Microsoft, and Mac OS, of course, it's developed by Apple company. So these three series of operating systems just have involved decades, and today we can see some descendants of these three series of operating systems. So for us, we just need to focus on the second one, because we need to learn how to operate it with commands. So about Windows OS, maybe most of us, but some of you are familiar with some other operating system, but in China, most of the people just they have been used to Windows OS, cause a lot of reasons. Anyway, you can see the history of the Windows OS. For now, we have Windows 10, right? Um, and because the smartphones just take have taken have taken place of a PC in many fields. Sometimes it seems like that we spend less and less time on computers and we spend more and more time on smartphones. But I think Windows, the operating system like Windows or Mac OS, they have their own scenarios to for some for certain people. So if you are interested in this different series of operating systems, it'd be better for you to learn some basic frames about Windows or iOS. So then we just move on to the fifth generation of computers. Uh, you can see from from the middle of the 90s, the smartphones just provided us a lot of choice. We can use smartphone to do a lot of things today, and it gets more and more space or apps to help us finish some jobs we cannot do before. So for this generation, uh, we don't have the details about the operating systems designed for the smartphone or the other embedded machines. But basically, no matter which operating system you are using, the basic principles are similar because they all need a CPU to run some code. They all need the memory to store the code to be fetched into CPU to run, and they all need some input and output devices to get the commands from the human being and to show the results back to the human being. So I think basically if you understand the principles in this on this course, you can understand the other operating systems for other devices. So that's the history of operating systems. And now let's move on to the next part, the computer hardware. Um, as I know, you haven't taken any classes about the computer hardware before, because you might take the class for data structures, discrete mathematics, and maybe even database. But maybe most of you are not so familiar with the computer hardware, the architectures inside the computer. So now let's just take a quick, not a quick, we need to take a close look on this figure, because we need to understand the objects to be managed in the operating system. As you can see in this figure, we just list some basic necessary components of a simple personal computer, such as CPU, responsible for the processing of the data by running some codes, such as a memory to store the data and the codes. Uh, and then the CPU can get this data and codes and to process this data by running those code. Um, and we also have the monitor, it means the screen. So you can see all of these four uh, parts, they are input devices or output devices. Keyboard is used to input something into the computer, and the hard disk drive can be viewed as input and output device, because all the programs and data they are stored in disk, and after you get any result, you might store the result back to the hard disk. So and monitor and printer, absolutely they are output devices, right? All these I/O devices, you can see there are some separated parts list here. They called they are called controller. So if you want to show something onto the screen, you need to interact with, I mean, this you means operating system. Operating system needs to interact with the video controller. If you want to get something from the keyboard, the operating system needs to interact with the keyboard controller. So each device has a controller to control the operation on this device. So this controller, we can basically they are the device consists of these two parts. The controller is it belongs to a certain hardware device. We'll talk about this later in more details. But for now, you just need to know each device has two parts. One is the hardware to operate the data, and the other part is the electronic part to control the hardware part. So first, let's take a look at processors. Uh, Processors it means just CPU, central processing unit. So everybody knows CPU is the core part, is the core component for the computers, because you use computers to do something, and which part can do these things for you? I mean, do things, it means just run some programs. Of course, it's CPU. CPU is a unit, is a component who are responsible to run, to execute some instructions, and these instructions can be can be a lot of operations on data. So we have to understand this concept first. It's called CPU cycle. In a CPU cycle, CPU will fetch instruction from memory, because all the data and code and anything relevant to the program is stored in memory first. CPU cannot get anything directly from the disk. CPU just gets the data from memory. So first, CPU needs to fetch an instruction from memory, and of course it's over the instruction and the data to be processed, to be decoded, or to be calculated, to be processed. The data to be processed are transferred over the bus, as we see in the in the last picture, in the last figure. So first, CPU needs to fetch an instruction from memory and then decode it to determine the type of the instruction and the operands. Operands means the data to be, you might need to plus them together, or you need to move some bits. So the second during for the second step, when the CPU decoded, it will it has to determine if this instruction is illegal. I mean, we just emphasize a lot of times that CPU has two modes, right? So when CPU gets an instruction to be executed, it has to judge if this instruction is what is allowed to be executed by the program in the CPU. It will check the mode, right? If it's kernel mode, no problem. You can execute any instructions from the machine. But if it's user mode, and it has to CPU has to check if this instruction belongs to the subset of the machine instruction set. If it's not, then this instruction will be denied to be executed anymore. So these are the basic 3 steps of for a CPU cycle. Also, we need to understand each CPU has a specific instruction set. It means different chips, different CPU has different instruction set. So it means but for our programmers, we don't need to focus on these details, because in the lower layers, operating systems will handle the difference. But for us, but for operating systems, they have to be aware about the different instruction sets from different chips, because when you buy a computer without operating system, the computers, the manufacturer of the computers, they have no idea what kind of operating system will be installed on this computer, right? So they might the hardware might be x86 or might be ARM. So the operating system needs to take account of the different instruction sets. So when we install any operating system on different computers with different CPUs, they can be compatible to the hardware. Also, in this part just lists us some common instructions in the instruction sets from different CPU. These are such as you can use one instruction to be responsible to load a word from memory into a register, or you can use one you can design one instruction to be responsible for storing a word from a register into memory, such as etc. But we don't need to focus on these details. We just need to understand that different CPU has different instruction sets. But no matter which kind of instruction set the CPU has, the kernel mode and the user mode are the same for the CPU. They have the CPU can recognize which instructions are should be denied in the kernel mode. And in CPU, except the chips to run the instructions, we have some more more components. It's called registers. Register. There are a group of registers in the CPU. The general registers, they are used to store the data to be processed by the instructions. So the general registers are can be the general I mean application programs. They have the permission to access these general registers because they need to put the data into it, and when the instructions are executed, they need to get the result back to the memory through by accessing these general registers. So these are the most important. These are very important components for the CPU. Besides this general registers, we have some other important registers which are used to control the whole process of the instruction in execution. For example, we need to use a special register called program counter to contains the memory address of the next instruction to be fetched. Because in one CPU cycle, you just we know it will it just fetches an instruction from the memory, but there are a lot of thousands, millions of instructions in memory. Which instruction should be fetched next? That's the question which should be answered by program counter. So we're gonna store the memory address of the next instruction to be fetched in this very important register called program counter, and we're gonna talk about this program counter a lot of times during the learning later. So you have to understand what the program counter is. And then we have a register to store the stack pointer. When you want to run a program in CPU, you have to push some data into the stack, right? So there are, we just said in modern operating systems, a lot of more than one programs are stored in memory during the same time. So each program will have its own stack to store the relevant execution data. In CPU, there must be a register to store the stack pointer, which points at the stack of the process or the program in CPU. So this is stack pointer register. This register just points to the top of the current stack for the process in CPU in memory. This is stack pointer, and then we should move on to the most important register in CPU, because PSW provides us a lot of essential or information to control the whole execution of the program or the process. It's called program status word. It's a word, so it's more than one bit. It has it depends on different how the status words, they have different bits presenting different information. The specific content of the PSW is up to different operating system, but the basic information such as the CPU priority, the mode of the CPU, its user or its kernel mode, and uh, some other control bits. They are all included in PSW for any operating system. So PSW, you can see this uh, user or kernel mode. The information about user or kernel mode is recorded in PSW. So when CPU fetch the instruction and decode this instruction and find it's relevant to I/O operations, and this instruction can be executed by only operating system. This instruction can be executed under only kernel mode. The CPU will check PSW. Will check the mode if the mode matches to the instruction, and decided to deny to execute it or just execute this instructions. So this is about the last register we need to learn, we need to understand. So that's the basic, you can say CPU, this central processing unit, it includes some registers for some important data, either data to be processed or the data to be used to control the execution. Also, CPU has the main part to decode and to execute the instruction. Inside that's the structure inside a CPU. But if we zoom out, we can see that there are already a lot of computers providing multi-core CPU or even multiple CPUs in the same computers. We have some CPU with 4, 8, or even more cores on one chip, or we can get 2 or more CPU in the same computer, and among those CPU there is a very special one called GPU. GPU actually it's a kind of CPU, because it just does the same thing as CPU. It fetch some instructions and decode it and execute it. But the difference is that GPU, they are usually used for some specific operations. They are good for many small computations done in parallel. It means, for example, if you want to render a picture, the picture can be divided into maybe 10 or 20 parts, and each operations on each part is exactly the same. So we can do them. We can render this picture in a parallel way. So that's the typical scenario we use the GPU to do. So that's all about the processors. You just need to understand the inside, the structure inside of a CPU. And for GPU and multi-core CPU, you just need to learn, take a quick look about it at it. It's enough. So now let's move on to the next part, the memory. So CPU is responsible for the instruction execution, and the memory is responsible to store the instructions and data to be processed in CPU. So memory, you can see memory actually it's a system. It has we can view it as a pyramid because we have different devices to store data or and programs. Um, if we want to store something in the computer, we hope that we can access the data very fast. We hope it can provide us a large volume, and we hope the price is very low. So that's the goals of the memory. But in the but the fact is we cannot have it's very hard for us to have a memory with all satisfying all these requirements. So you can see this you can check this figure to see we have a typical memory hierarchy. uh, in this figure we just see there are different layers of memory. When we say memory, if we don't emphasize if we don't emphasize what kind of this memory is, we usually mean it's main memory. In this in, oh, sorry. On this course, in the following chapter, you might hear me saying memory. If I just say memory, actually I want to mean main memory. But if I want to emphasize the difference between different memory components, I will see main memory, magnetic disk, cache, and registers. Okay, so if we just say memory, usually it means main memory. But here on this slide, we just talk about these 4 different layers, which all can store some data and instructions and programs and software, etc. So you'll see the registers in CPU. We just discussed it in the last part. CPU registers, we can access the bus. So if you want to get some data from the register, you can get it very soon, because the typical access time to register is 1 nanosecond. 1 nanosecond, usually it's around 1 clock cycle. So it's very short, it's very fast. But we can't just we can't have too many registers in the same computers, because it's very expensive, and there is no there might be no enough space for the millions of registers. So you can see usually we have less than 1 kilobytes of registers. So the registers can only store the data less than 1 kilobytes. So for registers, it's expensive, it's fast, but it's small. And for the cache, you can see the access time to cache is pretty fast too, and it has more capacity. So cache is the layer between registers and main memory. So and cache is actually sometimes cache is a special part in the memory, but we can use the hardware to it has the support from the hardware to transfer the data over the bus. We don't control the data access on cache through software. We use hardware to control this, so it's very fast and it's stable. But the capacity for the cache is not big enough. So it's just maybe it's less than 4 million bytes. Um, and next one is the main memory. So I don't know the capacity of your main memory. For mine, it's around just 8 gigabytes. Cause this figure is was presented in 2014. So maybe it's a little overdate, but today I guess maybe you will have 8 gigabits is enough for most computing for most computers, I think. And you can see the uh, typical access time is 10 nanoseconds, so it's acceptable. I think it's acceptable for us to wait for the data access, right? But if you check the uh, magnetic disk, you can see the access time is just million no kilo times, right? Nanosecond. It's just 1,000 times that than the main memory. So of course magnetic disk is very slow, but the advantage of the magnetic disk is it's very cheap and it can provide large capacity. Usually we can get even more than 4 terabytes of disk space through magnetic disk. And between the memory and magnetic disk, you can see there is one more layer called SSD, solid state drives, right? Because in most laptop notebook today, I think they just use the SSD. The magnetic disks are popular on personal computer or servers or frameworks, but usually for laptop notebook we just use SSD, and it's not so expensive as before. Also, it can provide up to maybe up to one terabyte. I'm not sure because mine has only my notebook has only 256. So that's the hierarchy about the memory. We just explain them a lot in, based on this figure. So we'll take a quick look about this about the following slides. You can see registers. Anyway, the upper layers, the upper layer, the memory is it's faster than the faster. It can get it means faster but expensive, more expensive, and it can get it has only less capacity. So registers is very fast. It can get the data in one clock cycle, and cache is very fast too, but it can provide more capacity than registers. And you can see this cache hit, this concept about cache hit. You can learn about this concept after the class. You can read the book and try to understand the cache hit, because it's a quite important concept, but we don't have time to explain about this concept now. So let's move on to the next part, main memory. Main memory, usually it's random access memory. And for the notebook, we know that main memory will lose all the data in it if the power is off. But for the smartphone, in our smartphones, uh, usually there are no separated main memory and SSD, or between memory and or there are no magnetic disks in smartphones. So no matter your phone is off or on, the data on your phone are stored permanently all the time. It won't disappear. So the main memory in the okay, so um I just recognize that maybe I'm not right. I'm not sure about the memory of the smartphones, because they might have different structures. If you are interested, I'll check it later to let you know the exact situation in smartphones. Okay, but for now, we if we focus back to the main memory related to the general computers, you'll see the data in memory will disappear after the power is off. So we have the ROM, this kind of memory, read-only memory, and the data stored in ROM can be stored permanently. It means even though the power is off, the data in the ROM is still right over there. So we just put some very important and essential information for the computer in this ROM. Usually we put the bootstrap loader in ROM, because even when you press the button of the computer, you need to turn on your computer, and there is nothing in main memory of the computer, because the main memory has nothing if the power is off. So when the power is on, when you turn on the computer, how can CPU fetch any instructions from the main memory? Because we know the CPU can fetch uh, you can only fetch instructions from the main memory. So we should put some important uh, programs in this kind of memory called read-only memory. That CPU, when the power is on, CPU just fetch some instructions from the ROM, and usually these programs are bootstrap loader. Uh, so that's about the main memory. And for the disks, actually, I think this figure, you might. I don't think it's necessary for you to grasp this figure by now, because SSD is getting popular. It is getting more and more popular, and the magnetic disks are useful in some maybe in some server and in some data centers. But for us, for common users, which have the laptop notebook, we the usage of the magnetic disk is getting less and less. So we just need to know that we don't focus on the detail uh, of the principles of how to operate this magnetic disk. You just need to know it looks like this inside the magnetic disk. It has the cylinders and it has different plates, uh, and in each plate there are some some tracks here, and we have three parameters to locate some data in the disk. The cylinder number and the plate number and the track number, and you can locate where the data is. It's here or here, because for the file systems, you need to install some files in the disk. You have to locate it, right? You have to know where it is. And for magnetic disk, it's just simply use the above three parameters to locate this data. And for the other details, we just ignore them here and move on. Let's move on to the next part. SSD, we don't have, in this textbook, we don't have, on this course, we don't explain too much details about SSD. You just need to know it's much faster than magnetic disks and more expensive. And speaking of the stability, I think now SSD is quite stable as compared to magnetic disk. So maybe in the future, SSD, I think SSD will replace magnetic disk, at least at least in the personal computers, in the laptop notebooks. So we just talked about CPU and memory. Memory includes the registers, cache, and main memory, and the SSD or magnetic disk for the data with large volume. And now let's take a quick look about I/O devices. So as I said, I/O devices, each device is connected to that bus, to the bus in the computer. They consist of two parts, the device itself and a controller. And we can recall the figure we just explained a lot before. So the controller is a chip. It's an electronic chip or a set of chips that physically controls the device, and the device itself just consists of a lot of mechanic parts, and you have to use the controller to control the device. For example, if you recall that this figure about the magnetic disk, you have to move these arms to move it left or to the right, move it in or out, and who can control the device to move the arm, its controller. So the controller is an electronic chip or a group of chips to control these behaviors on each device. Each device has, you can divide them into two parts. Each device has two parts. One is the device itself, and the other one is the controller, the electronic part. And who can control the controller? I mean, how does the controller know where to move, where to move in or move out, on which plate or on which track, how to know about all of this information. For controller, it has to receive the commands from the driver. Device driver, you have to understand this concept too. Driver is a kind of software, and cost it just needs to execute some key uh, operations on input or output devices. So this driver must run in kernel mode. And each device, uh, when the manufacturer produce a device, the device already has two parts, right? But it cannot it cannot work if there is no suitable software to control, to send the commands in the specific forms, in a specific formats so the manufacturer has to supply the manufacturer of the devices should be responsible to design a special software called driver to for each kind of operating system it supports. It's a long sentence, and I hope you can understand this. I mean, there are different operating systems, right? And if you recall the first figure we explained, the between the application program and the operating system, there is a layer called user interface program, right? So whenever the application program want to use the IO device to get some data or output some data to the device, it has to send the request through the user interface program to the operating system. And when the operating system gets the requests from the application program, the operating system needs to handle all the details about the I/O operations. But we have different operating systems. It means provides it has to this different operate so different operating systems, they need to send the command transfer the requests from the application program to the commands to the driver of the specific device. So here you can imagine there is one more layer between the operating system and the I/O devices. Here the I/O devices includes the I/O devices already include the controller. Controller is just a chip. They don't know what to do. You have to use the software called driver to tell the controller where to move, what to do. And how can the driver knows what to do? How can the driver knows where to get the data? It has to receive the commands from the operating system, right? But different operating system has different mechanisms, has different formats of the course. So the manufacturer has to understand or has to be aware different interface with different operating systems, so that each operating system can send the commands which is transferred from the request or from the application program, so that the operating system can send the commands which can be understood by the driver, and then the driver will be aware of what the operating system wants the device to do, which way, what kind of data will be loaded into the computer, or what kind of data will be stored in the device. Then the driver can follow the commands, and then the driver will transform the commands from the operating system to a certain to the commands that the controller can understand, and then the drivers just send these commands to the controller, and finally controller just executes the commands from the driver and to get some data or store some data. So the whole hierarchy is the application program sends the service request through interface program to operating system, and operating system transforms the requests service IO operation requests from application program into the command which can be accepted, which can be understood by the driver. And then the driver transforms the commands from the operating system and transforms the commands from the operating system into the commands which can be understood by the controller. And then the controller just do the real operation, the physical operation on the device, on the physical device. So this is how one single I/O operation is processed during in the computer. Okay. If you cannot understand the whole process, it's okay, because we are gonna talk about this in chapter 5. Yes, we're gonna discuss more details in chapter 5 about this whole process. So it's okay if you cannot get it right now. And so you already know the drivers are very important for the usage of devices, right? If you want to input or output any data, you have to interact with the drivers, right? So we have to understand there are 3 ways to put a driver into OS. We need to build the connection between the driver and the operating system. You must have such experience that you buy maybe you buy a printer, you buy a scanner, or you buy any device, and you have to install some driver, right? That driver is provided by the manufacturer of your devices, right? So how to install that driver? For now, it's getting easier and easier. Sometimes you don't need to implicitly to install the driver. Sometimes you just plug the device in your computer and you can use it. For example, if you plug a U-disk into your computer, you can just directly store or get some data through it. But if you have to install a driver, I mean, to connect to build the connection between the driver and the operating system, because the driver needs to receive the commands from the operating system, right? The driver, when the manufacturer provides the drivers for the devices, they have no idea which drivers, because each operating system will be relevant to one certain driver. Different operating system requires different drivers. So the manufacturer they just provide kinds of drivers for different operating systems. When you buy this when you buy a device, you have to build the connection between the driver to your operating system, to the operating system on your computer. So you can take a quick look about these three ways to put a driver into OS. After that, you can use that I input device or out device to do anything. So this is about I/O devices, the driver, the the structure of the device and the drivers relevant to the I/O device. And after we put a driver into OS, after we build this connection, we can actually use the I/O device to do some I/O operations. And there are three ways to finish some I/O operations. It's called busy waiting, interrupt, and or DMA. Again, I have to say, you can, if you are interested in these three ways for at this moment, you can read these words. But if you if it's if it's hard for you to understand them all, you can just keep it like this. You can just ignore them and wait until we move to the chapter 5, because we will have more details to discuss in chapter 5. Okay, next one is very important. Interrupt. We just explained the different components of a computer. All of those components are connected over bus, right? They use they transfer the data over the bus, the CPU. When you want to run some program, you need to load the data. You need to load the program and the data from the disk into the memory, and the CPU will fetch the instructions from the memory one by one. And after the CPU get the results, you just put the results back to the memory, and the memory will output results back to storing the data back to the disk, or just showing it, or by showing it on screen, or just playing it through the speaker. That's the whole cycle of a program it was performed. But during the whole time, you have to understand there are more than one programs in the computer, in the operating system. So it means if there is only one program, you want to load data from disk to memory, okay, just do it. You want to load instructions from memory to CPU, or vice versa, it's okay, because you just own all the resources. You can do what you want, whatever you want to do. But if there are more than one programs, and each program wants to load something from the disk into the memory, each program wants to run some instructions in CPU, needs to load the data from memory into CPU, or vice versa. There are problems. There are a lot of issues to handle, and that's what the operating system is used for. And if the operating system wants to handle all these issues, the interrupt must be used. So you have to understand this very important core concept. It's called interrupt. When multiple programs share exactly the same set of resources in the same computer, how to control them, how to coordinate the multiple programs share the resources based on interrupt. So we don't have time to explain about this concept today, but we're gonna continue explaining it the next class. Okay, I see the time is up, so that's all for today. And if you, I see there are only 5 students submit your answers. So, because it's the first time we publish the exercise on MOOC, maybe some of you have no idea how to how to get in it and submit it. So you can have a second chance at 10 p.m. today. I mean the Beijing time. You can log in MOOC before 10 p.m. I'm gonna publish the first exercise at 10 p.m. tonight. I'm gonna publish it again for those students who haven't submitted for maybe for any reasons. Okay, this is the first try, so I'm gonna give you a second chance. But for the later, for the exercises later, I hope you can submit them in time before the deadline. Okay, that's all for today. Thank you.